Hello, everybody. Welcome to today's lecture. Today we are going to start on chapter 3, which deals with probability. Okay, so probability is another branch of mathematics that maybe you've heard about, but it's also probably likely you haven't really studied before because it's not typically taught in the general math curriculum, right? It's like one of those specialty topics that you usually have to take a class specifically in probability and statistics or something like that in order to learn about it at all. But you probably have, encountered some things dealing with probability. For example, when you flip a coin, right, you know that you have a 50% chance to get a heads or a 50% chance to get a tails. So things like that are what we're going to be studying in this chapter. So let's first start by defining probability, which the book doesn't really do. So I'm going to just write my own definition here, borrowed from Wikipedia mostly. This is the branch of mathematics. Concerning how likely an event is to occur. Okay. So how likely is it that something's going to happen, essentially? So in the coin flipping example, how likely is it that we're going to get a heads? How likely is it that we're going to get a tails? Okay. And we're going to describe this numerically, right? A probability is always going to be a number between 0 and 1. Or if you're using percents, it's always going to be a number between 0% and 100%. So we're going to be working between 0 and 100% always. We're not going to be dealing with any negative numbers, and we're not going to be dealing with anything more than 100%. There's never going to be like an 150% chance that something could happen or anything like that. So let's start with some definitions here. Okay. Some definitions. Let me change that. So first definition, a random. Sorry, let me change that back. A random experiment. Okay. Before I write out this definition, I should point out that word random. That's going to be, what we're dealing with a lot in probability. We're looking at things that are random, which is why we need to know how likely are they to occur. Okay. So a random experiment is an activity or an observation whose outcome cannot be predicted ahead of time. Okay. So this is worded a little bit strangely. It's saying it's an activity or observation whose outcome cannot be predicted ahead of time. The way they're using the word predict here means that we can't say with 100% certainty what's going to happen. So with the coin flip experiment, that would be an example of a random experiment because we can't predict with 100% certainty what's going to happen, whether it's going to be heads or tails. There's an element of randomness to it. We can only be 50% sure of what's going to happen. So that's what they mean by cannot be predicted. So it's not saying predict how we normally use it. Usually when we say predict, we're saying like, okay, I predict it's going to rain tomorrow, which means, maybe we know that there's like an 80% chance it's going to rain tomorrow or something like that. Here, when they're using the word predict, they mean 100% certainty. Okay. We got 4 definitions here actually. So let's just go down the list. That was the first one. The next one is a trial. A trial is one repetition of a random experiment. Okay. One repetition of a random experiment. So, the example I gave for a random experiment would be flipping a coin. So a trial would be just flipping the coin one time. Okay. And then if you do it again, that would be your second trial. So it's just performing that experiment essentially. For another example, maybe a random experiment could be drawing a card out of a deck of cards, right? There's a randomness to that. You can try to guess what card it is or whatever. But that would be a random experiment because we can't say for certain what card is going to come up. A trial would be the act of drawing one card. Okay. Next, another important definition is a sample space. Okay. A sample space is the set of all possible outcomes for a random experiment. So let's look at how to write sample spaces, because this will be some of the questions you'll be asked, is how to write a sample space. So let's think about flipping a coin. Okay. What would the sample space be here? Well, it's just all the possible outcomes. So what are the possible outcomes when we flip a coin? We could get a heads or we could get a tails, right? So we would say the sample space, which a lot of times we write as S, but you might see it written as other ways, is equal to, with sets, this is a set, which means like a collection of things. We usually use the curly brackets. So we'd write S equals curly brackets, heads, comma, tails. So we just list all the possible outcomes. Okay. Or maybe if we use an abbreviation, we would say H, comma, T. Okay. So this is one example of a sample space. What if we flip a coin 2 times in a row? Okay. Now what's the sample space? We'll use H and T to denote heads or tails. So we could get heads both times. We could get heads and then a tails. We could get tails and then a heads. Or we could get tails both times. Okay. So the first letter here is the first toss. The second letter is the second toss. So HT and TH would be different, even though ultimately you have the same number of heads as tails. Okay. So this would be the sample space for flipping a coin 2 times in a row. So let's look at one more example. Let's say that we roll a 6-sided die. Okay. So we take a die and we roll it. What are the possible outcomes? Well, on the standard die, you would have 1, 2, 3, 4, 5, or 6, right? So you roll it and you get one of these numbers. Okay. Okay, so that's what a sample space is. So let's look at the next definition. An event is a subset of the sample space. Okay. So what does this mean if we look at these sample spaces up here? What does a subset mean, first of all? That means that you take part of the set, right? Usually not the entire set. So if we look at heads or tails, for example, one event from that could be heads, right? Because heads would be part of this set. Or another event could be tails, right? So typically we have our sample space and we're looking at what the probability of an event is, meaning the probability of something happening in that sample space. Or what's the probability of getting heads and heads in this sample space? Or what's the probability of getting a 3 in this sample space? Okay. So those would all be examples of events. The 3, the heads, the heads, maybe the 5, something like that. Okay. It doesn't necessarily have to be only one thing, too. Maybe we could say, what's the probability of getting a 3 or a 5? And then we look at a combined probability like that. So an event could be 3 or 5, or it could be getting an odd number, so 1, 3, or 5, or it could be getting an even number, or it could be getting a number less than 5, right? These would all be part of the sample space. All right, so let's look at one more definition here before we can finally write out how we would write the probability of something. Okay. An experiment has equally likely outcomes if every outcome has the same probability of occurring. Okay. So this would be something like with the heads or the tails, right? We know there's a 50% chance of getting each of them. And this is often the case. Like if we roll a die, there's an equally likely chance that we get a number, we get the number 1, we get the number 2, etc. Okay. So there's no, nothing's being weighted more than something else. Okay, so if we have equally likely probabilities, then, so in this case, the probability of an event, or an outcome rather, A. Okay, so we just call any of the outcomes A. So this could be like A could be getting a heads or getting a tails or whatever. In those cases, we might use H or T, which we write as P parentheses A, and we would read this as P of A. If you've taken like a college algebra kind of class where you looked at functions, you might recognize this as function notation, because that's what the probability is. It's a probability function. But we don't need to worry about that. We just write it as P for probability, and then in the parentheses, the probability of what we're looking at. Okay. Is P of A equals the number of ways for A to occur divided by the total number of outcomes. Okay. So the number of different ways that A could happen divided by the total number of outcomes. So let's look at an example here. The easy example, what's the probability of getting a heads? Okay, which we already know the answer to, 50%. Where do we get that? How many different ways, if we flip a coin once, how many different ways are there to get a heads? Well, based on our sample space we have before, there's only one way. There's getting a heads, right? Because there's only two things that can happen, getting a heads or getting a tails. And in this case, there's only one way to get a heads, which is getting a heads. It might sound kind of weird saying it like that, but if we think about a different example, like if we're thinking about flipping a coin 2 times and we think about, okay, what's the probability of getting exactly 1 heads? Now there's 2 ways for that to happen. It could happen here or it could happen here, where we have 1 heads in both of them. So it sounds kind of weird saying it like that since we only do have one choice, but it still works out. So the probability of getting heads is 1, because there's one way to get a heads, and then what is the total number of outcomes? Well, you could either have heads or tails, so that's 2. So 1/2. Okay. And this would be the answer, it would be 1/2. Now, if you remember from your developmental math class or an equivalent class, 1 divided by 2 is the same thing as 0.5. That's just writing the fraction in decimal form. And if we take that decimal and write it in percent form, we get 50%. Okay, so you just move the decimal 2 times over to the right. So you'll want to be comfortable flipping between fractions, decimals, and percents back and forth. Okay. So the probability of getting heads is 50%. And we also know, if we looked at the other one, probability of getting the tails, the same thing would happen. We get 1 possible way to do that out of 2 possible outcomes, which is 50%. Okay. What about the probability of rolling a 5? Okay. Well, there's one way to get a 5. That's that you get a 5, right? And what are the possible outcomes on the 6-sided die? Well, there's 6 things that can happen, so it would be 6. So our answer, our probability is 1/6. Okay. Now, when you're writing your answers, you can always leave it in fraction form. You can convert it to a decimal or percent if you want to. Normally when we talk about probabilities, we often use percents. But with the math, it's usually easier just to leave it as a fraction since it comes out naturally like this. What's the probability of rolling a number less than 5? Okay. So now there's more than one way for this to happen. If we look at our sample space, well, the numbers less than 5 are 1, 2, 3, and 4. Okay, there's 4 choices here. So how many ways could this happen? It could happen 4 different ways. We could get a 1, a 2, a 3, or a 4. How many total outcomes are there? There's 6. Okay. So the probability of rolling a number less than 5 is going to be 4 out of 6, or 4/6. You can simplify this to 2/3 if you want, pull a 2 out of both, or you can just leave it like this. And if you convert it to a decimal, you're going to get about 66.67%. Okay. The book talks about the round off rule, which says that you should give probabilities rounded to 3 decimal places. Honestly, I don't really see that happen very often. I think most of the time I see probabilities rounded off to 2 decimal places, so that would be fine. Or you can just leave it as a fraction, so then it wouldn't even matter. All right, let's think of one more example here. Let's think about a deck of cards. So some information about a standard deck of cards. Okay. There's 52 cards. There's 4 suits with 13 cards each. There's the numbers 2 through 10. And then there's a jack, queen, king, and ace. Okay. 4 each. I don't know why I capitalized those. Okay, so 4 of each of those. So like there's a 2, there's 4 of them, 1 for each suit. Okay, so there's the hearts, clubs, spades, and diamonds. So this is some information about cards. So let's look at, for example, what would be the probability of drawing a 2? Okay. So, well, how many ways are there to draw a 2? Well, there's 4 2s in the deck, so there's going to be 4 ways to do this. And then how many total possibilities are there? Well, there's 52 total cards you could draw, so there's 52 total possibilities. And then you could simplify this if you wanted to 1 over 13. Okay. What is the probability of drawing a number? Okay. Meaning one of the 2 through 10s and not a jack, queen, king, or ace. Okay, these are not considered number cards. These are considered face cards. So what's the probability of drawing a number? Well, how many possibilities are there? First of all, how many numbers are there? There's 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 9 cards. Okay. And there's 4 of each of them. So there are 9 cards and 4 of each of them. So if we want to count that, that would be 9 times 4. And then there's still 52 total things to get. 9 times 4 is 36. So this is 36 out of 52, which we could simplify if we wanted to 9 over 13. Okay. So on the other hand, what's the probability of drawing a face card? Well, if there's a 9 out of 13 chance of drawing a number, the other half of that, the probability of not drawing a number, well, that would be what's left of it, right? Because all together it has to add up to 100%. So 9 out of 13, the inverse of that would be 4 out of 13. All right. So there'd be 4 out of 13 probability of drawing a face card. We'll talk more about that later when we talk about complement probabilities. Okay. All right. All right. I think that we will end with just a few definitions here. So we're going to keep this video a little bit short today. So the first definition, this is like all the different kinds of probabilities, okay? So the first type of probability that we could have is a theoretical probability. Okay. So a theoretical probability is based on a mathematical model where all outcomes are equally likely. Okay. So this is like, okay, we can't really observe the data or observe the experiment. There's no way for us to actually physically do the experiment like there is for flipping a coin. So theoretically, we think the probability would be this. Okay. Kind of the opposite of this would be an empirical probability. Okay. Empirical means that it is seen or experienced. So an empirical probability is based on an experiment or observation and is the relative frequency of the event occurring. Okay. So a theoretical probability would be something like, okay, we write our sample space with our heads and our tails, and we see, okay, the probability that we get a heads is 1/2. If we actually performed an experiment where we flip the coin, say 10 times, and we get heads 6 times and tails 4 times, then the empirical probability would tell us there's a 6 out of 10 chance to get a heads, which is 60%. So empirical probabilities can lead us astray, but they have their place because we can't always make a mathematical model. If the idea is if we do the empirical probability enough times, like if we do the experiment enough times, the empirical probability will eventually reach the theoretical probability. Eventually, they'll be the same. So oftentimes, this is how we find out what the probability is by doing the experiment many times. And then finally, so the theoretical probability is the most reliable. The empirical probability is kind of the next most reliable. The least reliable would be a subjective probability. Okay. It is an estimate or guess based on experience or intuition. Okay. This is not a very reliable source of probability, right? Because everybody's different. That's what subjective means, is that it's kind of just your opinion. And there's really no place for opinion in something like this. So, but still, oftentimes, we're kind of pulled in to making guesses like this. It often leads down the path of what's called the gambler's fallacy, which we'll talk about later, which is that, okay, if I'm flipping a coin 10 times in a row and I got heads on the first 9, then I think the 10th is going to be tails because I'm due for a heads, right? There's no way I could get 10 heads in a row. But that's not true because the 10th coin flip, it doesn't matter what you got on the last 9. The 10th is still going to have a 50-50 chance of getting a heads or a tails. So it can lead to problems like that. That's called the gambler's fallacy, which we'll define later. But nonetheless, it can be helpful, if you have a probabilist who studied probability a lot and they kind of know how this stuff works, then this could be a good starting point towards where they would work to figure out what the true probability is. Okay, so we'll stop there today. Next time we'll start talking about certain rules for probability, like complement probabilities and what a probability distribution is. And we'll then start talking about um, probabilities for multiple events happening at the same time. Okay. So thank you for watching today, and I will see you then.